So we were talking about the reaction of an alkyne with HCl, and we looked at the transition state that is reported for the addition of the first halogen atom going to the secondary carbon. We all know that the partial positive is more stable on a secondary carbon. And then the second electrophile addition is also going to go to the secondary carbon. When we add chlorine, we don't change the substitution of the carbon. It still has only 2 bonds to carbon, and the other carbon, the CH2, has only 1 bond to carbon. So now when we add another equivalent of HCl to our halogenated alkene, that chloride ion is still going to add to the more substituted carbon. So it's also a regioselective reaction. Regioselective meaning that the addition of the atom occurs in a specific way. It's selective as to where it adds. Okay, and so because it's going to add to the more substituted carbon, that is why we end up with the geminal dihalide. Geminal meaning that both of the groups of interest, the chlorines, are on the same carbon. Okay. The formation of the more stable carbocation in this case accounts for the regioselectivity. A secondary carbocation, even a secondary carbocation with chlorine, is more stable than a primary carbocation. While chlorine would not like to donate electron density, it can donate electrons to make a pi bond to the positively charged carbon and become positive. But you should remember from your Lewis structure rules that we're going to put the positive charge, the best Lewis structure, has the positive charge on the less electronegative atom. And so out of the 2 options for valid Lewis structures, the positive charge at the carbon is considered the better Lewis structure. So this Lewis structure, this resonance structure is better than this other resonance structure, Lewis structure, that has the positive charge at the chlorine. And this arrow, this double-sided arrow, indicates sharing of electrons. And in Chapter 8, we will cover what resonance, we will review resonance. You should have learned resonance in Gen Chem. But we'll review resonance and what the sharing of electrons is and how we can recognize when electrons can be shared. One hint about sharing electrons is that electrons can only be shared to atoms. They can be shared from sp3 atoms, but not to sp3 atoms. So an sp3 atom can donate electrons to an sp2 or an sp atom, but electrons cannot be donated to an sp3 atom because it already has an octet. It already has a maximum number of bonds. Okay. The same reaction occurs with HBr. So the same reactions that we've been discussing with HCl occur with HBr, And now they're giving us an alkyne that is not symmetric. It's not symmetric, but both of the carbon atoms are equally substituted. So we have both pi carbons, both alkyne carbons are secondary. And so that means that this reaction is not regioselective because the carbons are equivalent. And in that case, we could get addition of hydrogen to either one, for an addition of bromine to either one. So we have to show both products. This unsymmetric alkyne will produce a product that adds both to carbon 1, 2, 3. So we will get one product that adds 2 Brs to C3 and one product adds where we add 2 Br to C2, so that we have 2,2 dibromo pentane as a product, and we have 3,3 dibromo pentane as a product, because the carbons are equally substituted. They're both secondary carbons. For a symmetric alkyne, we get that we can add 2 Br to C3 and 2 Br to C4, but if you draw those products, you should note that they are the same thing. What is going to happen is that it's symmetric, so when you number, you're going to give the chlorines the lowest possible numbering, and you'll see that they are the same thing. They are both 3,3 di, oh, it should be bromo, Br. They are both 3,3 dibromo hexane. And so they are the same molecule. So a symmetrical alkyne produces one product. Okay, now guess what? Cl₂ and Br₂, when we have only one equivalent, react with the pi bond in the same way that they reacted for the alkene. We form a halonium ion intermediate, and each of the pi carbons receives one halogen atom, so that we have vicinal dihalide. Once we've added one equivalent, if we then add a second equivalent, we can end up with a vicinal tetrahalide. So we have at one equivalent an alkene with 2 chlorines, and at 2 equivalents an alkane with 4 chlorines. So we can make with one equivalent, or 1-to-1 molarity, a dihaloalkene vicinal dihalo, meaning that they're not on the same carbon. But if we add 2 equivalents or excess, then we get tetrahalo, alkane, for our final product. We can do this with Cl₂ and Br₂. It's not possible with fluorine or iodine. You'll find out that we rarely use fluorine in reactions. Okay, so at 1 equivalent, we have an alkene with 2 halogens, and at 2 equivalents, we will get the tetrahalide, and that is for Br₂ in dichloromethane, but you have to remember that dichloromethane is only solvent and that it is a spectator. Okay, this is going to be trickier. Acid-catalyzed addition of water to an alkyne is trickier than acid-catalyzed addition of water to an alkene. For the addition of water to an alkene, we produced a more substituted alcohol. So we have the OH on a secondary carbon and the H going to a primary carbon, so that the hydroxyl group added to the more substituted carbon. For the addition of water to an alkyne, we have what we call an enol intermediate, so it adds in the same way. The OH added to a secondary carbon and the H added to a primary carbon. But enols are unstable, and so it rearranges to form the corresponding ketone. And so the change that you make is the position of the pi bond. Instead of having a pi bond between the carbons, you're going to move the pi bond to carbon to oxygen pi bond, and then all carbons should have a total of 4 bonds, so we move a hydrogen. So we added H to this terminal carbon, and we moved the pi bond. And that's how we got to the final product of the alkyne. But you're going to have to know more than that. You're going to have to know what the mechanism is. Okay? So whenever we form an enol, it is almost always going to rearrange to the keto-tautomer. The switch between OH and a carbonyl group is called tautomerization. And we're going to look at what tautomerization is. So we start at the point that we have the enol, and I can actually go back and show you the full mechanism. So before we got to the enol, what we had was our alkyne, RC triple bond, C8. Well, they're using an internal alkyne. So RCR. Okay? And what we did with that was that our pi electrons came and took a hydrogen from the acid. When we put H2SO4 in aqueous solution, we form hydronium ion acid and HSO4 minus ions. So here's our acid. the electrons from the pi bond go to the hydrogen of the acid. The pi electrons from that hydrogen go to the sigma electrons between the hydrogen and the oxygen go to the oxygen. And that gives us an intermediate and probably I should draw this as a pi complex. I'd rather not. With a protonated enol, oh, incorrect. With a protonated, the oxygen hasn't been added yet. So we have added hydrogen, but not the oxygen. So in the first step, we have our pi. Let's go ahead and draw it as a pi complex. Okay. So we would have C triple bond dash 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 3-membered ring to hydrogen dash 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 of the hydronium. Okay, and then we have, so we have this intermediate, then a molecule of water, H2O, will then donate electrons to make a bond at the more substituted carbon. These are actually both secondary, so it won't matter on this one. And then the pi electron density will go into forming the carbon to hydrogen bond at the other carbon, and we'll lose water as a leaving group. So that will give us RC double bond CHR, and then that carbon has a bond to water. Another molecule of water is used, and that molecule deprotonates here, giving those electrons to the alcohol. And at that point, finally, we have, when we get to here, the reaction arrow goes to the first step that they show. We've made the enol when we deprotonate the water that bonded to the carbon. Okay, so then tautomerization, looking at the tautomerization part, we have in tautomerization, our carbon-carbon double bond donates electrons to pick up a hydrogen from the acid. And when that occurs, the carbon that doesn't make a bond to hydrogen becomes positively charged, and oxygen donates electrons to eliminate the carbon positive charge and take on an oxygen positive charge. So now we have a protonated ketone. Another molecule of water will come and remove the proton, and those the bond electrons between H and O of the ketone go to the oxygen, and then that gives us our ketone. So this is the tautomerization step. And what it really is moving electrons around to make a new bond to hydrogen at one position and a pi bond between carbon and oxygen at the other. So our differences are, let's close, keep. So here what we have is we added this hydrogen to this carbon using this pi electrons. So now we have a new hydrogen at this position. And this lone pair in green makes this pi bond to carbon. The water atom, oh, I need to small eraser. Heck, not medium. Okay. The water molecule picked up, using these electrons, picked up this hydrogen, and then we sent this sigma bond to be a lone pair on the oxygen. Okay. So we have our new hydrogen here and our new pi bond here. And then we also have a new lone pair on the oxygen that came from the bond that oxygen had to water. But ultimately, the important changes are the purple and the green. And that's just looking at what tautomerization involves. So what I want you to be able to do is to look at an alkyne reacting with water and H2SO4 and making the corresponding ketone. For a symmetrical alkyne, we create one product because the double bond O, whether it's placed on carbon 3 or carbon 4, because it's symmetric, in the final product, it produces 3-hexanone. Whether I add it to this, okay, so if I added to the yellow carbon or to the green carbon a C double bond O, I would end up with 3-hexanone from either direction because it's symmetric. If you count from the end closest, it's symmetric. 1, 2, 3. So either way, the C double bond O adds to carbon 3 because it's symmetric. If it's unsymmetric, I will get an alkyne with an C double bond O at carbon 2, and I will get an alkyne, oops, Sure. With C double bond O at carbon 3. Because those are both secondary carbons. No. Seriously? Okay. Okay, there we go. So we get the 3-carbon ketone and the ketone with the double bond O at carbon 2. So those are our 2 ketones because the internal alkyne is unsymmetric.